Hello, this is Algebra 1, Lesson 3-3, Transforming Linear Functions. In this lesson, we will be able to graph transformations of linear functions by multiplying or adding specific values of k to the input or output of a function. And we'll interpret the key features of the graph of a linear function and use them to write the function that the graph represents. Overall, you'll be able to transform linear functions. Some vocabularies that you might want to look at is transformation and translation. Let's get started with critique and explain. Avery states that the graph of G is the same as the graph of F with every point shifted vertically. Okay. Cindy states that the graph of G is the same as graph of F with every point shifted horizontally. So they're arguing, is G shifted vertically from F like this, or is it shifted horizontally like this? Okay, part A. Give an argument to support Avery's statement. Does it look like Avery's statement, the first one, shifting vertically, works? Sure, why not? You see the same slope. It's moved vertically from each point +2, right? So if you just look at y-intercepts, even your y-intercept is moved vertically from 1 to 3. So you can use the y-intercept and of course other points to state and back up Avery's statement. Okay. But the first thing you should notice is that the lines are parallel. So yes, all the points, if it's moved vertically or horizontally actually, will be the same. So for Avery's statement, we can say that the y-intercept of F is 2 units less than of G. Okay. What about Cindy's statement? Could shifting horizontally also work? Yeah, if you look at this point over here, it could move 1 unit to the left. And if you look at this point over here, that also looks like 1 unit, right? And this one over here, 1, 3, also moves 1 unit to the left. So you can say the x-intercept over here of F is 1 unit to the right of the x-intercept of G. What do you know about linear equations that might support either of their statements? Okay, first of all, they're parallel lines. What kind of characteristics do parallel lines have? Yeah, they have the same slope. So they will never meet each other, which means could they overlap if they're moved or if they're shifted? Or in other words, translated. Yeah. So you can say equivalent expressions, equivalent linear expressions can be written in different ways. So it's possible to to have horizontal transformation or vertical transformation. So let's say to have horizontal or vertical. To make equivalent equations. Okay, so think about this case. And let's think about this question, this essential question throughout the lesson. How does modifying the input or the output of a linear function rule transform its graph? So we're going to modify some inputs or outputs to transform the graph. Are you ready? Here we go. Example 1, vertical translations of linear functions. The positions of two baby sea turtles making their way to the water after hatching from their eggs is recorded. They move at the same speed, with Byron starting 2 feet ahead of Frank's starting point. Oh, look, we gave them a name, right? So the left one is Byron, the bottom one is Frank. And once they're hatched, once their eggs are hatched, they run to the water. But there are a lot of dangerous things on the way because they're super tiny. It takes a long time for them to get to the water. And there's a lot of birds who would want to eat them. So a lot of them get eaten by the birds. Some of them just don't make it, right? So yeah, so if you look at the picture, they're almost there. Let's look at part B. What function represents each turtle's position as they make their way towards the shore? Byron starts at 2 feet and Frank starts at 1 feet and they keep moving. We're going to find the speed of each turtle by finding the slope of each line. The speed, how fast they would go, would be the slope. Like how far are they going in terms of each second. So we have distance for y, time for x. So that means they have a relationship. Okay, so Frank, the blue line, we can count 1 over and 1 up and 1 over. So rise over run, 1 over 1 is just going to be 1. Or you can use these points, 5, 5, and use the slope formula. Right? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1 would be your slope, considering 2 points. Okay, so 5 minus 4 is 1, 5 minus 4 is 1 as well. So that's going to be 1 over 1. Or if you chose the origin, then you would use this. 5 minus 0 over 5 minus 0 is 5 over 5, which is 1. Same thing for Byron. You pick 2 points to figure out the slope, and that's also 1. They have the same slope. So what can you tell about these 2 lines? They're parallel. Okay. Both turtles are moving at 1 feet per second. So the function f of x, which is Frank's distance from his starting point, which represents Frank's distance from his starting point, and g of x is x plus 2. They have the same slope, but that's his y-intercept, right? 0, 2. So it's x plus 2 versus just x, because it's x plus 0 for Frank. So x plus 2 will represent Byron's distance from his starting point. All right. Part B, what happens to the graph of a function when you add a constant to its output? Constant just means a number, okay, without a variable. So remember the equation of this line. Which one was g of x? I think that was f of x is equal to x. And Byron was g of x is equal to x plus 2. Okay. Because they have the same speed, Byron will always be 2 feet ahead of Frank. Right? So you can say that all these points from f of x would be translated up 2 units in order to be the exact same line with g of x. So adding a constant plus 2, right? X and versus x plus 2, that plus 2 matters. Adding a constant k to the output of a linear function translates the graph vertically by k units. Okay, so if you add 2 from the original equation x, you're moving all the points up 2 units. Okay, so let's try this question. Number 1a. We're gonna have f of x equal to negative 4x. How does the graph of g of x equals negative 4x minus 3 compare with the graph of f? So compare these graphs, f of x and g of x. Your original equation is negative 4x. How would you compare g of x, which is negative 4x minus 3, to f of x? Okay, we have the same term, negative 4x, right? So if you subtract 3 and your k is 3, remember this? You're subtracting 3 from all the points. What is it really doing? The graph is going down. Instead of going up, you're going down how many units? 3 units. So you're going to use the term, it's going to be shifted down. How many units? 3 units. Okay. Part B. What about negative 4x plus 1.5? How does it compare to the original f of x? It's shifted up or down? Up. How many units? 1.5 units. Okay, so output, adding a constant to the output just simply means this whole thing is a rule for your output. So we just add a constant k. If k is negative, you go down. If k is positive, you go up. You will learn later how to add constant to the input, but adding a constant to the output is you have to learn that first because it's easier and less complicated. Let's go over some definitions. A transformation of a function f maps each point of its graph to a new location. Okay, so each point means all the points move the same way in a new location. Okay, one type of transformation is translation. A translation shifts each point of the graph of a function the same distance. A translation may be horizontal or vertical. You can move up or down, that's vertical. Okay, up or down. And horizontal would be left or right. Okay, that's horizontal, that's vertical. Make a note on that if you're confused with horizontal and vertical. Okay, so if you look at this graph, this could be a vertical translation, it could go up. If you look at this one, this could be a horizontal translation when you go right. Depending on how you see the graph, it could also be defined with horizontal translation, and this horizontal translation could also be defined as vertical translation going down. Okay, but the rules, how you write out the exact rules, are going to be different for horizontal and vertical, and you will know if it's horizontal or vertical by looking at the rows. Okay. Let's look at example 2. Horizontal translations of linear functions. How does adding a constant k to the input of a linear function affect its graph? Let's consider these graphs for f of x equals 2x minus 4 and g of x equals 2 times x plus 5 minus 4. What do you notice about the values of f of x and g of x? Looking at the table. Okay, if x is -4, you plug it into f of x, you plug it into g of x, right? And then you get different values. If x is -4, f of x would get a -12 for the output. So this is a point on f of x, -4, comma -12, right? But g of x will have a different point for a -4. If your x is -4, you have -2 for your output. Okay, and so on. So if you get the same x, you'll get different answers for different equations. Okay. Oh wait, yeah, I'm sorry, that's when x is 1. When x is 1, g of x will be -2. When x is 2, g of x will be 0. But look at the other points for 1 and 0. This is 1, comma -2 for f of x. Okay. And you have 2, comma 0 for f of x. So you can get the same points when you substitute a different value that follows the rule here, x plus 5. Okay, if your x is -4 and you add 5, that's 1. If you substitute that to g of x, and then and that's when you get 1, comma -2. Okay, you can graph the functions, right? The graph of g of x, the graph of g is the graph of f translated 5 units to the left, right? So if they translate, this is when they translate, they will have the same points, right? But right when you just plug in x values over here, you will start with different points, right? So when you plug in 0 for f, that's 2 times 0 minus 4, so that's -4. But if you plug in 0 in g of x, that's 0 plus 5. So 5 times 2 is 10, and 10 minus 4 is 6, right? So then, oh yes, this is when your x is equal to 0, and that's when your, oh wait, my first x's were right. Yes. So, and this is when 0, comma 6 comes into your g of x. Okay. So you may think that a positive value of k here would shift it to the right, but how does the graph change? It moves to the left from f of g. So remember, your f is 2x minus 4, and your g looks very similar, but what's different? You added a 5 in your input. This is how you add a constant for your input instead of output. And you've already started with a -4 constant added on your vertical translation. This is the horizontal translation where you go left. Okay, for horizontal translation, if you add 5, that means you're going to the left, because you have to subtract k in order to get go right. Okay, x's and y's are flipped because this equation is written in terms of output. Okay, so if you're thinking about input, you have to think backwards. All right. So yeah. So adding a constant k to the input of the function translates the graph horizontally by k units to the left. Okay, if it's positive, to the right, if it's negative. Let's try, well, because k is positive, if k is positive, it's going to be subtracted. So if it's subtracted, you go right. If it's added like this, plus 5, it means k is negative, so you go left. Okay. Try number 2, part A. How does the graph of g of x, which is 3 times x minus 4, plus 7 compare with the graph of f? Compare these two rules. You have 3x plus 7 for f of x, and then g of x is exactly the same except the negative 4, right? 3x plus 7, but you have to subtract 4 first. So that's a translation for horizontally, right? So then you're going to shift how many units to the right or left is the question. So this is, it must be x minus k, right? So is k positive? Yes, because it's x minus 4. Just looking at k, k must be, k is 4, right? So k is positive. So this graph is shifted 4 units to the right. Okay, what about this one? X plus 9.5. What is k? K must be negative 9.5, so that if you subtract negative 9.5, it becomes positive. It becomes plus 9.5, right? So then you shift the graph, how many units? 9.5 units to the left because k is negative. Okay. Let's look at example 3 on the next page. Stretches and compressions of linear functions. Okay. Part A, how does multiplying the output of a linear function affect its graph? So we're done with adding and subtracting constants. Okay, those are translations. Now, what if we multiply some numbers? Okay, let's look at this example. We're going to compare the graphs of f of x equals x plus 1 and g of x equals 4 times x plus 1. So we're going to take the entire rule and multiply all of it by 4. And that is a vertical transformation. Which type of transformation? We're going to talk about it later, right? It's called the stretch, and it's a vertical stretch. It's either a stretch or a compression. Okay, this is a dilation if you multiply, but you need to know if it's a stretch or a compression. Stretch means it's getting larger. Compress means it's getting smaller and narrower. Okay, so we're gonna look at this and compare the numbers. Look at the table of values. These are some points. Your f of x has negative 3 comma negative 2, negative 3 comma negative 2, right? Your g of x will have negative 8 for negative 3. So it's like way down there. Okay, let's look at 0. 0 comma 1 for f of x, right? That's your y-intercept. 0 comma 4 is your y-intercept for your g of x. But wait, wasn't the graph of g of x way down there? when it was -3, when x was -3, and now it's above graph f, right? So what happened? The slopes look like they're different. You see that? Which one is growing faster? Which one is steeper? You can notice that graph G is a lot steeper than graph F. So from F to G, what might have changed? It's a stretch. It's a vertical stretch. Okay, and this is the scale factor compared to the original function. If you multiply the whole function with a constant, with number that's greater than 1, that's going to be a stretch because all the values are going to get bigger by 4, right? You multiply by 4. Okay, so it's a stretch. If the numbers get bigger, if the values get bigger for your output, that's a vertical stretch. Okay, what about this one? How can we multiply the input? Okay, we multiply the output here. We're multiplying the input here. Okay, compare these graphs. X plus 1 is your original graph, and then we have 3x plus 1. What's the difference with the multiplication of the output? You're only multiplying x. You're not multiplying the whole function, right? That's when you have an input. And for input, you always have to think in the opposite way because your graph is written in terms of output, like you're looking at the output. It's easier to look at the output, right? It's written in terms of output equals a function, right? So if you're thinking about input, you need to go backwards and think backwards. Okay, so if you multiply 3 and it's greater than 1, what does it do? Let's look at some numbers. Okay, when x is 0, f of x is 1. And g of x is also 1. They start at the same point. If x is 1, f of x would have 1, 2. G of x will have 1, 4. Okay. So it seems like the values get bigger, right? But we're not looking at the outputs. These are all outputs. What is the input, right? For output, for every output, you need to get a smaller input. Does that make sense? So if you look at the outputs and compare the outputs here, 4 and 4, right? In order to get 4, f of x needs 3 as their x. G of x just needs 1. So from 3 to 1, your input got smaller. So you're comparing the input now, okay? Looking at your outputs. Your input got smaller. So that means horizontally, what does it mean? Does it stretch or does it shrink? It's a compression, it shrinks. Your numbers get smaller, right? So this is a horizontal compression from F to G. Horizontally, you're looking at horizontally. If it horizontally stretches, it goes that way. Horizontal compressed means it gets compressed horizontally like this, right? So this graph got compressed horizontally. Okay, so if you multiply 3 into the x, that means it's compressed horizontally by the factor of 3. And that is called the scale factor. Okay, whatever constant you multiply with would be the scale factor. So let's try number 3. We're going to start with f of x is equal to x minus 2. Okay, from this, we're going to identify the compression and stretch. Okay, you have to be specific about horizontal or vertical. Is it a horizontal stretch or is it a horizontal compression And the vertical, is it a vertical stretch or is it a vertical compression? Okay, so use the words horizontal or vertical. And is it a stretch or is it compression? You also have to specify which scale factor, by the scale factor of what, right? This is the phrases and vocabularies you need to answer and describe the dilation, the horizontal and vertical compressions and stretches, okay, when you multiply. This is when you multiply, okay? So part A. How does this graph of g of x compare with the graph of f? What do you notice? What's different? X of 2, x minus 2. Look for x minus 2. You have x minus 2. And then you have something different over here, 0.25. First of all, is this a change in output or the input? It's the output, right? You multiply 0.25 for the whole function. So this is an output change, which means it's going to be a vertical dilation, right? So how do you know if it's a stretch or compression? You look at the values and see how the numbers change, okay? If it's less than 1, you're going to get a smaller value, right? If x, so this is g of x, okay? If x is 0, g of x is 0 minus 2, so negative 2 times 1.25 is times it by 1 over 4. So negative 2 over 4 would be negative 1/2, negative 0.5, okay? What about 2? 2 minus 2 is 0, so g of x is 0. And what about f of x? What was f of x? If x was 0, f of x was simply negative 2. If x was 2, f of x was simply 0, right? So 2 comma 0 would be the point that they have in common. But look at 0 comma negative 2. From negative 2, your values became smaller. So you would say, oh, this is a vertical compression by a factor of 0.25, okay? How does the graph of g of x, part B, 0.5x minus 2 compare with the graph of f, okay? We have 0.5 here. Is this multiplied to the whole thing or just the input? This is just the input. You do not have the parentheses, so you don't have to multiply 0.5 out with negative 2, right? It's just with the x, okay? And let's look at some table of values. When x is 0, what's the new g of x? Negative 2, okay, that's still good. 2, next is 2. You have 1 minus 2, which is negative 1, right? So you have to look at more points. What about 4? 2 minus 2 is 0, okay? So look at this. In order to get the same 0, okay, what does your x, now we're comparing the x values, okay, because this is a horizontal dilation, okay? From 2 to 4, because you're starting with f of x, and then you're going to g of x. Compare the values of your input, 2 to 4. In order to get the same value, 0, what does your input have to be? It gets bigger from 2 to 4. So this is a horizontal stretch, okay? Horizontal stretch by a factor of 0.5, okay? So you can describe the horizontal and vertical stretches and compressions looking at the points and comparing the points and the values, okay? For vertical, you need to compare the outputs. For horizontal, you need to compare the inputs. Okay, just keep that in mind. All right, so let's summarize our lessons. Transformations of linear functions. In this lesson, we learned how to translate and shift each point of the graph and be able to identify how they're translated vertically or horizontally. And also, we learned how the graphs could be stretched or compressed by scale factors of k, right? Constants. So some recap: vertical translation would be adding k to the entire function. Horizontal translation would be adding k or subtracting k to the whole only for the domain. Okay, vertical stretch and compression would be multiplication for the whole thing, whole row, and horizontal stretches and compression would be just multiplying a constant to the domain. Okay, so that was lesson 3, transformation of linear functions. I will see you in the next video. Bye.